Here we want to learn nonlinear dependencies between variables, potentially millions of variables. So if we have two variables, so there is a measure called maximal correlation. What it does, it finds best transformations of two variables, phi1 and phi2, such that their correlation is being maximized over all functions with mean zero and variance 1. So this maximal correlation measure can infer nonlinear dependencies that we could have missed if we use linear correlation measure. For instance, in this example, x1 and x2, they're nonlinearly related to each other, and if you use the linear correlation, you will get almost zero. But if you apply this optimization and find the best transformations, you can not only infer their nonlinear relationship, but also you can infer these functions that represent their functional dependencies. All right, but this was for the case of two variables. Now here we are dealing with problems with potentially millions of variables. These variables may be connected over a graph, like a gene network, social network, but if you don't have any constraint, you can assume there's a complete graph, so you don't have any graphical constraint here. So if you naively apply this pairwise maximal correlation, so what you are going to get is that each variable will be assigned to multiple transformation functions depending on its interactions with the neighbors. So x1 because of x2 will be assigned to one function, and because of x3 will be assigned to another function. It will be very hard to interpret, and it will also cause overfitting issues in some applications. So the key idea we have here is to find single transformation functions of these variables, mathematically we are showing here, such that the total observed correlation over the graph is being maximized. Again, the maximization over all functions with mean zero and variance 1. So this optimization, this is what we call network maximal correlation, that tries to identify these possibly nonlinear functions of each variable that the total correlation is being maximized. But this optimization is over all functions again. These functions, they are measurable, mean zero and unit variance. But we don't have any prior knowledge about the shape of these nonlinear dependencies. So the idea to solve this optimization is as follows. So we use basis expansion over Hilbert spaces. So for each random variable, we define a Hilbert space as a subset of all measurable functions with mean zero and bounded variance. And using that, any transformation function of a variable can be written as a linear combination of some basis functions. And if we use this representation in this optimization, it simplifies NMC optimization to an optimization which is over real vectors. So this is basically the way that we tackle this optimization, and we can actually use this framework to even rederive the results of the pairwise correlation. Now it turns out that this optimization is fundamental in different aspects, and when we apply it to different setups, it tells us about some fundamental understanding of the underlying graphical models as well. So for instance, if we look at NMC, this optimization, over nonlinear observations of jointly Gaussian variables. Suppose you have some latent variables you don't see, and you have some nonlinear observations of them, and you don't know these functions. All right, so if you apply NMC optimization over Y variables, this is a complete graph because you don't know the graph structure. What it gives you? It gives you transformations of these variables, right? These are GI stars. Now let's use these transformations to form a covariance matrix and an inverse of the covariance matrix, which is a precision matrix. So the theorem that we have here is that this precision matrix characterizes the graphical model of Y variables exactly. And the transformations that we find here completely recovers the latent variables, the underlying latent variables, without even knowing these Fi functions. But we need to have some conditions that these Fi functions, they are bijective, and the underlying correlation structure, we have this constraint that the sum of the correlations is greater than the sum of the square of the correlations, meaning that most of the correlations are positive, but you can have some negative correlations as well. All right, so the proof is basically using this idea. So first we shoot the basis functions. Here we use Hermite-Chebyshev polynomials because they form orthogonal bases over Gaussian density function. And if we use this, in this optimization, massage it, a little bit, we get an optimization like this, that we show that under that condition that I described, the optimal solution assigns all the weight to the first basis. All the other coefficients, they are zero. So what it implies that, so the first base corresponds to the identity function. This is this line here, right? And what it tells you that basically that's the latent variable that you are trying to infer. So the optimal transformations that you find here recovers the latent variables even without knowing these fi functions. Like this is some simulations. So these are 4 variables. These are nonlinear dependencies between latent variables and observed variables. They can be arbitrary, even not need to be continuous, not need to be monotone. This is the true covariance. This is the covariance that you use, you compute using observed variables. Use y variables without ignoring nonlinear dependencies, you get something like this, which is different. But if you apply this optimization and compute the covariance using the transform variables, you get something like this, which is basically recovering the underlying covariance even without knowing these relationships. And this is another method that we did for the comparison. So this is just the case that we have the distributions, right? But in real life, we have samples from these distributions. We have empirical distributions. So we also look at how many samples we need to have a guarantee of computation of NMC. We have some other results. This was one example for categorical variable, how you can compute again the best transformations of these variables. What are the iterative ways of solving this optimization in linear time? What are the distributed way of solving this optimization? So it's also interesting. So here, the objective function that we consider was the sum of the inner products. Basically, this is the correlations between the transformations, right? So what if in an application, you don't care about the sign of the correlation? The positive and negative correlation, they are the same to you. So you put an absolute value here, right? So that's the absolute NMC that you can, again, use the same methods to solve it. You can add more regularization terms, if you don't want to, you have a few samples and you don't want to overfit. So I want to also highlight one of the real data applications that we used. So we have applied this NMC over cancer data set. These are the RNA-seq for different genes for different cancers. This is one example of nonlinear dependencies that we identify between genes in this cancer type. These are the dependencies that you couldn't observe using the linear covariance analysis. And after we infer this graph, we infer this nonlinear gene module. These are the subset of genes that are highly nonlinearly interacting with each other, but you don't see this using a linear covariance analysis. And then we want to see if it makes sense, if it has any biological interpretation or not. So this is up until here, we were just doing math and algorithm, and we have this inference. So to validate some of these findings, we do this experiment. So we divide cancer patients based on having or not having this gene module, this nonlinear gene module. If they have a high expression of that module or low expression of that module, to 2 equal size groups. And we look at the survival times of these cancer patients to see if they're significantly different in the 2 groups or not. And in some cases, for instance, in this case, we see a significant difference between the survival times of the two groups. So the blue ones, they are the ones with high expression of the module. The red ones, they are the ones with low expression of this module. And if you ignore this partition, you get like the middle one. And you see there is a significant difference between the 2 curves, indicating that if there's a cancer patient that it has this module, high expression of this module, it's gonna probably not survive, more than like 500 days, almost 2 years. With a high chance, those patients, they don't survive. It's a way of validating that these modules, the nonlinear modules that we can't find using the linear covariance analysis, they may have they may reveal some, underlying biology that we couldn't see using the other methods.